Swayam Prabha. Digital India. Educated India.
Welcome back to the discussions on the concept of stresses and strains. Now, until now, we have looked at the normal stresses and the normal strains, or the longitudinal stresses or the axial stresses, one and the same thing. In this particular lecture, we are going to look at the shear stresses and the bearing stresses which are there. Now, before we go into looking at some of the very practical examples of these shear stresses or the bearing stresses, first we are going to learn that how these stresses look like, how they act, what kind of deformations they induced, and then we will move on to understanding that some of the very practical applications, and you will be surprised that around you there are n number of materials which are undergoing these kinds of shear stresses, and it's just the right time to start looking for them. Now, first I will bring you back to this particular slide which we had looked before, where a person is exercising in the gym, and what we had done is that we have sort of taken this particular system that is there, a portion of this equipment, and even segregated a smaller chunk of that one, and within that even a one more smaller chunk, right? And once we were looking at that, we saw that this particular element, if we have to segregate the different forces and the stresses which are acting over here, we have the normal stresses which we have looked at, and also the shear stresses which are acting along that particular surface of this element over here. Now, in addition to that, remember we had mentioned that on the hand we have these contact stresses which are acting, right? When you're holding, this is the contact stress that you're applying. So we are going to take a look at that as well, right? Now, coming back to the shear stresses, from the nature of how it looks like, shear stresses are those which act along the surface of an element. Now, remember that when we had looked at normal stresses, these stresses act perpendicular to the cross section of the element. Shear stresses act along the cross section. For example, for the same sponge, or if you have a loaf of bread, or if you're trying to cut through a cube of butter, right? When you are cutting through, these force which you're applying, if I have to cut this one across that entire cross section, this particular force acts. So shear forces always act tangential to that particular cross section. If I'm cutting it all across this cross section, I'm going to cut, during my action of cutting, I am going to induce a force which is acting along the cross section of that particular element, right? Now, similarly, if you maybe, and you have probably done this inadvertently at your homes, if you have a thick book, for example, say this one, this is one of your textbooks again, the mechanics of materials. If you have a thick book and if you're trying to apply a particular force, the sides which were initially vertical, after you apply that force, you see it has a certain angle, it has a certain slant over that, right? Now, similar kind of things are utilized in civil engineering structures as well. For example, the one that you see on your screen are the bridge bearing pads. Now, remember, these bearings are different than the bearing stresses which we are going to look at. This is a pure structural element, although conceptually it is more or less the same, but we'll come back to this later. Now, the whole purpose of bridge bearing pads is that if you have a force which is acting on the top surface of the pad, right? Now, you might wonder that in bridges, these bearing pads are, kept on top of the column. So you might be wondering that these bearing pads should always take the vertical force, which is coming from the gravity weight of the bridge, or the weight of the pedestrians or the traffic and so on. So in what kind of cases do these bearing pads have these kinds of, horizontal forces, or the forces acting along the surface? Well, think of earthquakes, for example. During earthquakes, you have the bridge girder, which is, moving in the along the longitudinal or along the transverse direction. During that time, the forces are these kinds of forces which are acting on the surface. Or temperature stresses, as the beams continue to expand or contract, you will have the forces which are acting along the surface. Now, remember the discussion we had on the rollers, right, which allows some amount of deformation? Well, these bearing pads serve a similar kind of a purpose. For example, when this particular load V that is applied over here, it undergoes some kind of a deformation like this. So the faces which were vertical before and after this particular force is applied, it undergoes a certain angle change. Now, remember that stresses, shear stresses, normal stresses were designated by the Greek symbol sigma. Shear stresses are designated by the Greek symbol tau. right? Now again, remember stresses, how do we define stresses? Stresses are forces divided by the area on which the forces are acting. So in this case, if this particular force is V, this V acts over this area A times B. So my tau is going to be V divided by A times B, right? So this is the shear stress in a crude form. We'll see there are more elaborate formulations for the shear stresses later, but on an average, so if I have to just write on an average, right, that is V divided by A times B, right? Now if we take this particular element and we sort of discretize it even further, how does it look like? So if you take this element, remember the total deformation of any civil engineering structure is the sum of the deformations of the smaller elements within the structure. So if you take a small cube in that particular element, this deforms like this. So again, initially the faces which were vertical, now it has a certain angle. Now if you take just this small element and look at it critically, it looks something like this. You have this tau over here which is acting on the top. Now you may be wondering that where did all the other forces come into play, right? Now see that from the perspective of equilibrium, if we have this tau 2 over here, you must have a force which is acting in the opposite, equal and opposite direction, right? So you have this one must also be equals to your tau 2, right? Now we have the additional forces which are developing, which are tau 1 over here, and this is the other force tau 1. Now you might be wondering that why this tau 1 force comes into play. Well, it's quite simple. Now if we have this tau 2 and tau 2 over here at the top and the bottom, these are equal forces which are separated by a particular distance, remember? So it induces a couple, a moment. Two equal forces separated by a distance induces a couple. So you need a balancing couple for that one. That is the reason that these forces tau 1 and tau 1 originates. Now, can you think of a relationship between tau 1 and tau 2? Yes, maybe many of you got it already. So first, let's take a look at the relationship, or if there is a relationship. So if this is the stress, remember you cannot take the, for a couple you need to, for a moment or to calculate a couple you need the force. You cannot do it with the stress, right? So if we have this tau 2 over here and this tau 2 over here, the net force acting on this face or this face over here is going to be tau 2 times the area. So you have tau 2 times A times C, right? And this so this is the force which is acting. So if I have to construct the couple over here, so this is the force that is acting, so this is maybe the force, right, times the distance B, right? This guy must be equals to tau 1 times, so the force acting on this particular face is tau 1 times B times C, right? And the distance between this face and this opposite face over here is A. So must be equals to tau 1 times B times C times A, right? So you have this ABC over here, that cancels out. So eventually you get your tau 2 must be equal to your tau 1, right? So these stresses are essentially complementary. So it's amazing. So if you have one tau over here, that in turn goes to generate all these different forces which are in this particular element, right? So this is what we looked at, that your tau 1 must be equal to tau 2, which may be, if you make it equal to maybe a tau over here, so this may be, said in an equivalent form. This is something like this, right? So you have a tau acting at all the different faces of this particular element, right? So what does that lead to? That leads to this this notion that shear stresses on opposite and parallel faces are equal in magnitude and opposite in direction that you have. Right now, there is a convention for shear stresses. At this particular moment, it is not important, but it's okay if you just go through that one. There is a sign convention, and it may read a bit hefty, but it's easy. Just stay with me, and I'll explain to you what it says. Let's just chop it off into smaller segments so we understand. It says a shear stress acting on a positive face of an element is positive if it acts in the positive direction of one of the coordinate axes. So let's just stop there. But it says a shear stress acting on the positive face of an element. What do I mean by a positive face of an element? The positive face of an element is if the outward normal points in the positive direction. For example, here you see this particular face, the outward normal of that, if this particular face is this one, the outward normal, again my right hand rule, points in the positive y direction over here, right? So on this positive face, so I have identified my positive face. On this positive face, my tau 2 acts in the positive x direction. So tau 2 is a positive shear force. See what it says, a shear stress acting on a positive face, my positive face is this one. It is positive if it acts in the positive direction of one of the coordinate axes. So it acts in the positive direction, so it's a positive shear. Similarly, this one over here, this particular face, the outward normal is along the positive x direction. So my face is positive and the shear force acts along the positive y direction. So this shear force is also positive, right? Now let's move ahead. It says that and negative, if it acts in the negative direction, we don't have any case over here, but let's go to the next statement, then you'll understand better. A shear stress acting on a negative face of an element is positive. So first let's identify what is a negative face. This face, this bottom face, is a negative face. Why? In the bottom face, the outward normal again points to the negative y direction. So on this particular face, you see this tau 2 acts along the negative x direction. So this tau is positive. So it is like two negatives make it a positive, something like that. The face is negative and the tau 2 acts in the negative x direction. So it's a positive tau. Yeah, so if you take a look at this particular figure over here, all the stresses are actually in the end positive. The ones which are in the positive phase are acting in the positive direction. The ones which are in the negative phase are acting in the negative direction. So two negatives makes it a positive, right? Now, similarly, as you can understand, that as we had for our normal stresses, which induce the strain, which induce the longitudinal strain, shear stresses also induce a kind of strain, right? So this strain looks something like this over here, right? So shear stresses, so shear stresses undergo a change in shape, right? So you have whatever was rectangular, now you have a change in shape over here. So whatever was straight over here, now you have a change in angle over here. You have a maybe a gamma by 2 over here, a gamma by 2 over here, right? And the whatever was pi over 2, this was 90 degrees to begin with. Now it is pi over 2 minus this particular gamma, right? So this particular quantity that you have over here is known as the shear strain. This is represented by the Greek alphabet gamma. For the normal strain, it was the Greek alphabet epsilon. Now you have the Greek alphabet gamma, and it is typically measured in radians or degrees. Now again, compared to the stresses, there is a positive convention for this. What it says is that the shear strain is positive when the angle between the two positive faces or two negative faces is reduced. Now remember, again, this was a positive face, this was a positive face. So in between these two positive faces, this angle has reduced over here. So it is a positive shear. Similarly, for this negative and this negative, this has reduced. So it is a positive shear. Right? So overall, you have this figure, you have a positive shear stress and a positive shear strain. Again, these are rules of thumb, these are definitions, these are not super important at this point of time. As long as you are, while solving problem, you have a sense of how the element is deforming in the end. If you write your answer in terms of the strain or the stress with a positive identifier that along which direction it is acting, it is completely fine, because different textbooks and different researchers, different academicians tend to follow different kinds of relationships, right? So now we have looked at tau, which is the shear stress, and gamma, which is the shear strain. Now, do you think that tau and gamma are related? You probably studied this earlier as well. Similar to the normal stresses, which is the sigma and epsilon. Remember, sigma was E times epsilon, the Young's modulus. In a similar way, analogically, there is a relationship between the tau and the gamma, which is this particular relationship over here, that tau is related to gamma in this particular form. The tau equals to G times gamma, where G is the shear modulus of elasticity or the modulus of rigidity. E was the Young's modulus or the modulus of elasticity. This one, G, is the modulus of rigidity or the shear modulus of elasticity. Now, there is a relationship between the G and E, and there is a way to derive that. We may look at it later in one of our later chapters, or if you're interested, standard textbooks, not in this particular chapter, as you go advance some of the advanced topics, when you talk about I think stress transformations or how the changing the face of a particular element changes the stresses. You can take a look at this one. Maybe we will come back to this later, but this is a relationship between the modulus of rigidity and the Young's modulus as G equals to E by 2 times 1 plus nu. Remember what nu was? Nu was nothing but the Poisson's ratio. So this was the Poisson's ratio. What is Poisson's ratio? Poisson's ratio is the ratio between the lateral strain divided by the axial strain. So this is the Poisson's ratio. Right. So now do we have an understanding on the tau, that is the shear stress, the shear strain, how they're related, right? Now, let's look at some practical examples. I've already told you some of the practical examples of the shear stresses, how they appear. For example, the ones which are, when you're cutting a loaf of bread, or if you're taking a book and giving it a slide, right? Let's look at some of the practical civil engineering examples. Again, I'm going to bring you back to something that you're familiar with, but you are familiar with only at looking at how the elements behave. You haven't looked at the ends of the elements. What I present to you are trusses. So trusses, you have already looked at these particular elements, remember, where we had discussed only the axial stresses which act. But if you take a look at the ends of the trusses, where you have always assumed them to be pin jointed, remember, it's always a pin jointed truss. In the pin joints over here, if you take a look into the zoomed in view of any of these joints, and if you look at a practical life example, do you see these smaller blocks that are there? Let me maybe change the color of my pen so that you can see it better. So these guys over here, these ones, right? So these are the bolts that you see. So all the bolts that you see over here, all of these ones over here, they are actually undergoing shear stresses, because if you think about it, this member is actually pulling into the bottom member, and these bolts are actually undergoing shear stresses. So let's take a look, let's take a further look into some of these bolts so that we understand better. Right now, first I am going to show you an example of this particular bolt which you see over here. Now we'll come back to why it is called a single shear later. So if you see in this particular bolt over here, if you have a bolt, right, which is connecting two plates, this plate A over here and this plate B over here, and if you are pulling this with force equal and opposite forces F, how do you think that this bolt is going to fail? This bolt is going to fail about this particular line. Right? So if it is simply, now imagine if this bolt was not made of steel or something like that. If you simply give it a good pull, you will see that if it's made of some very soft material, and if you attach it to one plate over here, one plate over here, and if you give it a pull, you will see that this fails along this particular axis over here. Right? Now again, remember, if my whole system is in equilibrium, the individual smaller parts must also be in equilibrium. So if I come back and if I draw the free body diagram of this particular one, this F over here along this particular surface, so if you have to take a cross section of the bolt, and if you have to look, so this particular surface is probably a circular section over here, right? So if you take a look over here, all along this particular this section, this force P is acting along this particular section, right? So from equilibrium, your P must be equal to F. Now this is the top part of the bolt. The bottom part of the bolt, if I have to maybe simply draw it over here, right, and this is the cap of the bolt maybe, right? If I have to draw it over here, this P will have an equal and opposite P which is acting over here, and this will be balancing this F. All parts are in equilibrium all the time. So you have a top P, you have a bottom P, you have a top F and the bottom F, right? So anyway, as you can tell over here, that this P must be equals to F, right? Now if this cross-sectional area has an area of A, right, then what is my tau? Remember, tau is nothing but is a stress. It is the force which is acting on that particular surface, on the cross section of the bolt, force divided by the area. So tau, I'm going to call this tau average, because later you will see that this is not exactly a true representation. This is a representation, it's an average sense. So tau average is going to be P divided by A, which is nothing but equals to F divided by A over here. Right, so this is the average stress which is acting on the bolt. Now since this bolt has one plane of failure, this is called a bolt in single shear. Right, now another example of a bolt in single shear, for instance, if you have a steel eye section like this, and if you put a bolt and if you are pulling it, say maybe this is a spanner, if you are just pulling it over here, if you look in another view, so this is the bolt, this is the back section of the bolt you're looking at, so this is essentially the same thing, right? So when you're pulling it, this bolt again has one single plane of failure, so this is also a bolt in single shear. Now if you take this bolt and if you draw the free body diagram over here, you have this particular force that is acting, so this may be equals to, the equivalent force is P, which is this P over here, right? And you must have an equal and opposite force P at this particular point, right? And again, the line of failure is this particular line or this particular line over here. So if you again segregate that one, if this is the shear force which is acting on this surface, now again if I have to draw how this cross section looks like, maybe it's a circular cross section, right? Maybe if I have a particular A, and this V, remember if this was my P, this V must be equals to P, right? So you have tau equals to V divided by A, or again tau average, right, equals to P divided by A, right? So this is another example of the bolt in single shear, right? Now a very practical example, a real life figure. If you take a look for a bolt like this, how does it fail? As I told you that it fails along this particular plane. Now this is a real life example. As you can see that in this particular example, sorry, maybe I just should write the P slightly below here. So this is the P, right? In this particular example, you see this is the plane of failure which is acting, right? So this is the, this particular plate maybe have been here and this particular plate may have been here, and the bolt tends to fail about this particular axis over here, right? Now next, what I'm going to present to you are bolts which are in double shear, right? Now again, you have a system of the bolts and plates over here. So you have one bolt which is EG and another bolt HJ, where there is a plate C over here, a plate A, plate B, and a plate D. And what you're essentially doing, you're pulling it, with two maybe equal and opposite forces over here. So the whole system is in equilibrium, right? Now, if you have to go and look a little deeper into this, so essentially again remember that if your whole system is in equilibrium, the parts must also be in equilibrium. So if I maybe take a peek into this particular bolt, the bolt HJ over here, if I just segregate that one, and now let's take a look at the free body diagram of that particular bolt. What you have as you're pulling it, now remember you have to visualize this one to a certain extent. As you're pulling it over here, right, this particular section is now going to undergo some particular force F, as you can see. Now as you pull it, and as you pull it from here, this plate C is going to have some resistance about this particular point, and this plate D is going to have some resistance over here. So you're going to have an FC and an FD. For the plate C it is FC, for the plate D it is FD over here, right? Now I have to ask you that for this particular bolt AJ, what are the planes of failure? You can clearly tell me that. Remember, again, imagine if this is made of a very soft material, and if you're pushing it, and if pushing it along this side with this force, and you're pushing it here with this particular force over here, you can tell that the failure planes will be along these particular axis over here, right? So essentially, from symmetry of the structure, suppose if I say FC equals to FD equals to this P over here along, and this force is this force F again, right? What we have at the top and the bottom along these particular lines, along this particular line, along this particular line, again you have this P, and this is the force over here. Now from this small chunk, can you write the equilibrium for that one? Yes, you can. How does the equilibrium look like? You have P plus P must be equals to F, right? Or your 2P equals to F, or your P equals to F over 2, right? Now if in this particular bolt has a certain cross section again, which is say A, what is my tau which is acting? Tau is nothing but P divided by the cross sectional area A. Now if I substitute that, it is F divided by 2A. Again, this is tau average, right? So can you in some sense get some a feel that which is probably a more safer bolt, whether a bolt in double shear or single shear? see for the bolt in the double shear that we had, my tau, let me go back, tau was F divided by A, tau average was F divided by A. Now if you go to the bolt in the double shear, which is this one, my tau is F divided by 2A. Right, so that one was F divided by A, this is F divided by 2A. So the bolts in double shear are essentially subjected to half the stresses of the ones in single shear, right? So it is always sort of preferable to have the bolts in double shear because they can, resist better amount of loads, or the amount of stresses they are subjected to is lesser than the one in the single shear, right? So now that we are exposed to what are the shear stresses, next what I'm going to talk to you are the contact stresses. Now remember what I told you, contact stresses are the stresses which you simply induce by contact, right? So and you do this every day. For example, when you open the handle of a door, right, you're essentially applying contact stresses. But let's again look from the perspective of the bolts which are there. So if you take a look at the bolt which we looked at in single shear, remember, right, if you have this bolt CD over here, and if you're pulling this with a force F and equal and opposite force over here, so this bolt A is applying a force over here, and this bolt this plate A is applying a force on this particular face, this plate B is applying a force on this particular face over here. Now if I just have to focus on this particular plate A over here, how does it look like? This particular plate A looks something like this over here, right? Remember, when I'm pulling it from here, this bolt is facing a force F, which is acting about here, right? And in turn, it applies this particular force P, which is equal and opposite to this F over here, right? So it is very similar to just imagining, for example, if this is my bolt and say my hand is my plate over here. If I'm pulling this, right? If I'm pulling this, the bolt applies an equal and opposite force to my hand, because the bolt is not going anywhere, my hand is not going anywhere, I am just simply pulling it over here. So whatever force the bolt gets, it applies an equal and opposite force to my finger, which in this case is the plate, right? So this one applies an equal and opposite force over here. So now this is important, over this entire thickness of this plate A, this curved surface that you see over here, you have this force P that is acting. So remember, just as I said, what is the bearing stress? Is the contact force. So this contact is happening over this entire curved surface over here, right? So if I have to again zoom it and look a little bit further, right? If the thickness of this plate is T, which is maybe this one, right, and if this particular diameter is D over here, so ideally if you have to calculate the contact stresses, what should it be? Again, stress is force divided by the area. Ideally what you should be doing is you should be dividing this force P divided by the area of the curved surface. But just as an approximation to just make life easier, what people usually do, they take the rectangular projected area of this particular, let me just draw it, of this particular face that is there. So that rectangular projected area is nothing but D times T over here. So bearing stresses or contact stresses are usually designated by this symbol sigma of B over here. So that is going to be equals to P divided by D times T over here. So this is the bearing stress or the contact stress, right? It is simply induced by the contact of one particular element with other, right? So we have looked at the normal stresses, the shear stresses, and the bearing stresses. Now, before we leave this particular topic and move on to the next one, I'm going to introduce one more important concept, which is very important for structural designers and which in many ways makes a lot of sense. That is the concept on the factor of safety. So what does the factor of safety mean? Factor of safety is essentially, for example, if you're building a structure and the person who is building it, you will ask that person to keep the stresses below a particular level. So you give him a value of the allowable stress. Now this allowable stress may be several times lesser the ultimate stress that element can bear, right? So let's say the element can bear a stress of maybe 20 MPa, but you ask the designer to construct a particular structure such that the stresses never go beyond 10 MPa, right? So what is the factor of safety, quote unquote safety you're inducing? It is 20, which is the ultimate stress that particular structure can take, divided by 10, which you have allowed the designer to design the structure for, right? So simply factor of safety over here, which is this particular factor N, N is the ultimate stress divided by the allowable stress. So the ultimate stress is always higher than the allowable stress. And how to get the ultimate stress? Ultimate stress is simply the factor of safety times the allowable stress over here. And why do we need this? Now, we need this not because we want to make uneconomic designs, but for several of these reasons listed over here, right? So suppose you are sometimes seeing very unprecedented loads which you have not designed your structure for, right? For example, once in a lifetime flood event occurs, or once in a lifetime a very strong earthquake occurs, which you have probably not designed your structure for, right? So even in those instances, such that your structure can maintain some minimum level of safety, the allowable stresses are kept below the ultimate stresses. So even if you reach some ultimate stress, your structure might be able to survive that particular earthquake or that particular flood, right? Okay, so with that note, we are going to end this particular topic on the concept of stresses and strains. I hope you enjoyed it. As I said, that the main objective of this chapter was to look at just individual ingredients, again taking you back to the kitchen, where we have learned what is turmeric, what is coriander powder, what is mirchi powder, and so on. So now we are going to go to the recipes. We are going to look at what are the different kinds of loadings for which these different kind of stresses may occur, right? So with that being said, I am going to close this chapter, and I will see you guys sometime very soon.